Characterization of incentive-compatible mechanisms. In section 9.3, we saw how to implement the most natural social choice function, maximization of the social welfare. The question that drives this section is, what other social choice functions can we implement? In economic settings, the main reasons for attempting implementations of other social choice functions are increasing the revenue or introducing some kind of fairness. In computerized settings, there are many natural optimization goals, and we would like to be able to implement each of them. For example, in scheduling applications, a common optimization goal is that of the make span, completion time of the last job. This is certainly a social choice function that is very defined. Then maximizing the total social welfare. How can it be implemented? Another major motivation for social choice functions that do not maximize social welfare comes from computational considerations. In many applications, the set of alternatives A is complex, and maximizing social welfare is a hard computational problem, NP-complete. In many of these cases, there are computationally efficient algorithms that approximate the maximum social welfare. Such an algorithm, in effect, gives a social choice function that approximates social welfare maximization, but is different from it. Can it be implemented? Chapter 12 and parts of Chapter 11 address these issues specifically. This section limits itself to laying the foundations by providing basic characterizations of implementable social choice functions and their associated payments. Because of the revelation principle, we can restrict ourselves again to look at incentive-compatible mechanisms. Thus, in this section, we revert to the notation used in subsection 9.3.3, the mechanism n equals to f, p1, p2, p3 until pn, over domain of preferences v1 multiplied by v2 and so on multiplied by vn, such that vi is a subset equals to r to a, is composed of a social choice function f, which maps the product of v1, v2, v3 until vn to a, and the payment functions p1, p2, p3 until pn, where pi maps the product of v1, v2, v3 until vn to r, is the amount that player I pays. In the rest of the section, we will provide the characterizations of when such mechanisms are incentive compatible. Direct characterization. We start by stating explicit the required property from an incentive compatible mechanism. The mechanism is incentive compatible if and only if it satisfies the following conditions for every I and every V minus I. First, the payment PI does not depend on VI, but only on the alternative chosen f of VI V minus I. That is, for every V minus I there exists price PA in R, and for every A in A, little a in capital A, such that for all VI with f of VI V minus I equals to A, we have that P of VI V minus I equals to PA. 2. The mechanism optimizes for each player. That is, for every VI, we have that f of VI V minus I is in argument max of VI of A minus PA, where the maxima is taken among all A, and where the quantification is over all alternatives in the range of f of dot V minus I. Proof. If part. Denote A equals to f of VI V minus I, A prime equals to f of VI prime V minus I, PA equals to P of VI V minus I, and PA prime equals to P of VI prime V minus I. The utility of I, when telling the truth, is VI of A minus PA, which is not less than the utility when declaring VI prime. VI of A prime minus PA prime, since the mechanism optimizes for I, i.e. A equals to f of VI V minus I, is in argument max of VI of A minus PA where the maxima is taken among all A. Only if part, first condition, if for some vi prime f of v minus I equals to f of vi prime v minus I, but pi of v minus I is greater than pi of vi prime v minus I, then a player with type vi will increase his utility by declaring vi prime. Only if part, second condition, if f of vi prime is not in the argument max of vi of a minus pa, the maxima, where the maxima is taken among all A, fix a prime in argument max of vi of a minus pa, where the maxima is taken among all A, but a prime is not the maxima, in the range of f of dot v minus I, and thus for some vi prime. A prime equals to f of vi prime v minus I. Now, the player with type vi will increase his utility by declaring vi prime.